Okay guys, so I'm going to start by going over the worksheet that I assigned to you guys last time. These are the answers I got. I put the points, the coordinates of the points here. So you guys can see the y values, which represent the heights of the rectangles. And then for this one, the bases were all 0.5. So if you do base times height, you get all these areas, you add them up, and you get about 4.25. This one, I don't remember what, I think it was like 6.25 if I remember. So that was an overestimate because there was extra area on top. This is an underestimate. So we know now that the area would be somewhere between 6.25 and 4.25. Okay? Maybe you could average them if you wanted to, right? Let's take a look at number 3. I titled it A Better Approximation. I called it a better approximation. Sorry, I got a little bit interrupted there with something. But anyway, I titled this A Better Approximation. And you'll notice that there's more rectangles, okay? So I'll let you ponder why I called it a better approximation, number 4. But for now, anyway, these are my best shots at what the points were. This was kind of tedious. I didn't like doing it either, but there it is. And then the y values there all represent the heights. Now, something you might not have noticed is that the bases of these rectangles are different now, right? Instead of having a base of 0.5, these bases are 0.25. So you would do 0.25 base times each height. And these would be the areas that you would get as a result. Adding all those up, you get this. Okay, now why is that a better approximation? Well, for one, remember how we said this was too much, this was too little? Notice this is in between, so that's good. But number 4, I'll let you guys ponder, why is that a better approximation? What would you have to do to get an even better approximation? Okay, well, the reason is because when you have more rectangles, look at the white space here, the leftovers. That's where our error is at. That's why these rectangles don't actually tell us the exact area under the curve. They're a little bit off because it's not a perfect filling in, right? But the interesting thing is the more rectangles you have, the better approximation you have. All right, so let's go ahead and take a look at part 2 then. For each problem below, you're given the derivative. Find out what the original function was. Okay, so I'm going to tell you guys the answers here so you can check your work. You should have gotten for this one x squared, right? Because if you took the derivative of x squared, you would end up with 2x. The next one, the answer would have been x cubed, because the derivative of x cubed is 3x squared. Tried to make it a little bit harder as we went. This one, well, what's the answer? Well, we multiplied something to the front and we got 6, and then we took 1 away from the exponent. So the exponent used to be 3, and that's what I must have multiplied to the front. So I multiplied the front by 3 and I got 6. So what was the front to begin with? It must have been 2. Okay? And then finally we have this one. That must have been 4x. Anytime you take a derivative, you just get a number. It's because it was a constant multiple. And then the last one here, it could have been any number. There's different answers for that. So, but anytime your derivative is 0, that means that whatever was there must have been a number. It could have been 5, it could have been 6, it could have been 1.2, could have been a million, whatever you want. Okay, and actually, since that's the case, instead of putting a number there, what we do in calculus, we just put a c, and that represents constant, some unknown constant. And in fact, every one of these could have had a constant, because when you take the derivative, the constant just goes away, right? So every one of these could have had some unknown constant associated with it. Okay, so there's your answer. Now, why did I do this? Well, believe it or not, part 2 has something to do with part 1. Okay, I'd made a boo-boo, so I had to rewrite these. But so what I was doing was I was showing you guys what part 2 has to do with part 1, right? So here's what it is. Part 1 is all about finding area under the curve. So for instance, let's take this one right here, f prime of x equals 4. Well, let's graph the line y equals 4. Let's graph that really quick. That's a horizontal line that is 4 units high. So that the line y equals 4 looks like that. Now, let's say that I wanted to find the area between that line and the x-axis from 0 to 5. So I want to find the area from here to here. Well, that's pretty chill. It's just a rectangle, right? So the area of a rectangle is base times height. My base is 5. The height is 4. And so the area of that rectangle is 20. That's just geometry. But I want to show you guys that calculus will actually do the same thing for us. Now you might think, well, that's kind of pointless, Mr. Bailey. Why learn calculus when you can just do geometry? Well, bear with me for a minute and I'll answer that question. So, let me show you guys how calculus can answer the question. Okay? Interesting thing, it's not obvious, but if you want to find the area under, that's not what I wanted to do. If you want to find the area underneath of a line, right, from one number to another number, here's how you would do it. You would find the integral of that number. So what's the integral of 4? We've already found it. It's 4x plus c. Now you don't need to include the c for this process, but just bear with me here. So what you're going to do is you're going to take the integral of that line, and what you're going to do is you're going to plug in two numbers, the left limit and the right-handed boundary. The right-handed one comes first, the left one comes second. So we get 20 minus 0 is 20, and there it is. So interestingly enough, there's another way to find the area. Instead of using geometry, you can integrate the function, which gives you 4x plus c. Find out what the integral was. This is what we call the integral. Plug in the right and left-handed numbers that are the boundary points for it, and subtract those results, and you get the area. Let's do another one. Once again, I still haven't answered the question though, so why bother with this if we have geometry? Well, I'm going to do another geometry example, but the only reason I'm doing this is to show you that what we're doing works, but I'll do a final example to show you that geometry is not enough. Okay, so let's do another one. Let's do this one over here. So let's say I wanted to find the area between the graph of 2x and the x-axis. So let's graph this. So let's say I had the graph y equals 2x. If you graph that, 0 is the origin, the slope is 2. So I'll just do a couple of points here. And there's that graph right there. Now let's say I wanted to find the area between 0 and 2. Well, that just so happens to be a triangle. And the area of a triangle, once again, is easily solved using geometry. We do the base times the height, 1, 2, 3, 4, it looks like 4, divided in half. And so the area of that region is 4. So the area under this line, between that line and the x-axis, from 0 to 2 is 4. But once again, I'll show you that calculus can do that. Instead of using geometry, I'm going to take the integral, which is x squared, and I'm going to plug in the right-handed boundary and the left-handed boundary, and I'm going to subtract them, and lo and behold, I get the area again. Okay, so now I'm going to answer the question for you. Mr. Bailey, why are we doing this when we have geometry? Well, first of all, it's faster, in case you haven't noticed. I don't have to graph it, yada, yada, yada. But here's another reason. There's some you just can't do. For instance, let's do this one. Un momento, I made a boo-boo. There we go. Still recovering. Okay. So, let's do this one. Suppose I wanted to find the area under the curve y equals 3x squared. Well, if you graph this, what you're going to end up with is you're going to end up with some kind of a parabola. It looks something like this. And let's say I wanted to find the area from, -2 to +2. In other words, I want to find the area between that parabola and the x-axis from -2 to 2. Well, we have a problem now. This is a curving line. And in geometry, we don't have a way to find area of curved things unless it's a circle. And this is not a circle, it's a parabola. So we can't use geometry to do this one. But we sure as heck can use calculus. What I can do is I could take the integral of my function, which is x cubed. I can plug in the right-hand number and the left-hand number, and I can subtract them. And I find out that the area is 16. Okay? Now, why does that work? I'm not telling you why it works. I'm just telling you that it works. We won't actually be learning in this class why that works. We could, but it's not going to be helpful for our purposes in this class, and it's actually quite complicated. So we're going to leave it off, but I will say that that's what it is. So we talked about part 1, estimating area underneath of curves, right? Well, it turns out that doing the opposite of a derivative, which we call an integral, doing the opposite of a derivative actually helps you get an exact answer for the area under a curve. Okay? And so, without any further ado, we'll go ahead and jump into our lesson and bring this stuff to life. So our objectives for the day is hopefully by the end of the day you guys can tell me what an integral is. Next, you should be able to tell me what all the parts are, because the way that we write an integral, there's some notation that we use, and there's a lot of little symbols we use. Hopefully you guys can look at all those symbols and tell me what all those symbols and notations mean. So, and then next, we're going to actually start doing some integral problems. Okay? So the first part is really just an introduction to what it is and how to write it. The second part, we'll actually start doing some integrals. So let's go ahead and begin here. What is integration? Well, for now, it's the reverse of finding a derivative. It's the reversal of the process of differentiation. Okay? So for differentiation, if I gave you guys x squared plus 5 and I asked you to find the derivative, you would get 2x. Well, with integration, I give you the 2x and I ask you, what was that before I took the derivative? And it's x squared plus some number that we don't know. Or maybe there was no number there at all. Who knows? Okay. Here is the symbol that we use for the derivative. Now, in order to help this slide make a little bit more sense, let's start off with our warm-up. So on our warm-up today, I asked you guys to take 2x. I said, okay, 2x is what my function, the derivative is. What was the function before I took the derivative? And we got x squared, right? Well, here's how we can write this using this new math notation. This is what we call the integrand. And this is the symbol that we use to represent the fact that we want to do the opposite of a derivative. We want to undifferentiate it. We want to find the original problem before it was differentiated. Okay? So that's my integral symbol. And now this thing that we used to call the derivative, now it's going to get a new name. We're going to call it the integrand. That's called the integrand. Now you guys remember back in our last chapter, remember how we talked about finding the derivative with respect to x? That told you what variable we were applying the rules to. Well, in the same way, when you do integration, you can also do that with respect to x. So we're always going to have a dx there or something like that to integrate, to indicate what we are finding the integral with respect to. Now the answer I get by undifferentiating this thing called the integrand, the answer that I get is what we call the antiderivative. It's called the antiderivative, which makes a lot of sense, right? If it's the opposite of a derivative, antiderivative makes a lot of sense. You could also call it the, and we'll talk about this one a little bit more later, but for now we can also call it the indefinite integral. So it has two different names. And don't forget, there could have been a number here before we took the derivative. It's just that they go away when you do take the derivative. And that's what we call the constant of integration. The constant of integration. So this was the derivative, and this is what it was before we took the derivative. But we're not going to talk like that anymore, because that's chapter 1 language. Now we're in chapter 2. We're talking about integration. So now I'm going to say this is the integrand, and this is the antiderivative. Here's my constant of integration. Here's the integral symbol. That's my indication that I need to take an integral. I need to do the opposite of a derivative. And then this thing here tells me I'm doing it with respect to x. That's what we call the variable of integration, by the way. In this case, x would be the variable of integration. If I were to change these to a's, then my variable of integration would be a. Okay? So there it is. So we talked about how we're going to talk about what is an integral. So let's stop there. What's an integral? Well, it's the opposite of a derivative. And then the next thing we say we're going to talk about is what are the symbols? Can you interpret it? Okay. This is our integral symbol. This is the integrand. This is the variable of integration. This is the antiderivative, and this is the constant of integration. So now, here's what I would encourage you guys to do. I'm going to give you guys another one from our warm-up today. From our warm-up today, remember I told you that f prime of x, we had this. I want you guys, and our answer, the answer we got was this. I want you guys to rewrite this statement here using this notation, just like I did for the 2x and x squared pair. See if you can do that. Pause the video here and see if you can do it. Okay, there it is on the right side of the screen. So I'm going to ask you guys some questions, and I want you guys to answer these in your head as we go. What is the antiderivative of this problem here? What's the antiderivative? It would be this. What is the variable of integration? It would be x. It says dx, so that means my variable of integration is dx. What is my integrand? 3x squared. Okay, before we move on, I want to give you guys one more thing. Suppose I gave you this then. And I want you to fill in the other side. Pause the video and see if you guys can figure that out. What would the other side be for that? So hopefully you guys took a moment to think about it there. So this symbol tells me to do something. This symbol means that this is a derivative of something, and I want to undifferentiate it. The way we say that is we find the integral. So what was this before I took the derivative of it? Well, we did it on our warm-up. We decided that that would have been 2x cubed plus c. There has to be some c there because we don't know if there was a number there to begin. But there it is. Let's do one more of those. Try this one. Well, actually, let's do two more. But you try to complete this statement now. Pause the video here and give it a shot. Once again, from our warm-up, we already know the answer. It's 4x plus c. But now I want to give you guys one that's not on our warm-up, just to kind of pull everything in together here. So suppose I give you guys this. What's the integral of 10 x to the, well, let's just say 10x. See if you can finish that statement. Pause the video and give it a try. Now, if you guys can't do this yet, it's okay. I'm going to give you a strategy to help you out with it in a minute, but I'm just trying to make you guys think a little bit here. Okay, so, well, this is the derivative, and this is the antiderivative. So the power here is 1. Well, that means before I took the derivative, then the power must have been 1 more than that. And I multiplied that number times the front, and I got 10. So what would I multiply by 2 to get 10? Well, the answer would have to be 5. Okay. Now, if you guys aren't getting this stuff, that's okay. Like I said, I'm going to give you a strategy in a minute. But there you go. So I just want you guys to get used to the notation and what it looks like for now. Okay. Just pulling all these thoughts together. So we've already done a lot of those. We'll skip that. All right. So here's the rule. Okay. Here's the rule. Here's our power rule that we talked about earlier. This year, we talked about how to find the derivative of a power function. So what you do is you take the power, you multiply it to the front, and then you subtract 1 from the power, and that gives you the derivative of the function, the slope of that function. Well, this is the power rule for derivatives, but if we just work backwards, that's what we call the power rule for integrals. It's the same thing, it's just working backwards. So let's take a look at that. First of all, let's go back to our derivative here. What do I do? Well, in this case, we subtract 1 from the power, and we multiply by n, right? So not surprisingly then, to get from here to the antiderivative, what we would do is I would add 1 to the power and divide by that value instead of multiply. Over here, we subtract and multiply, whereas over here, we add and divide. Okay? So, to go from a function to its antiderivative, you're going to add 1 to the power and divide by that value. Okay? So, for instance, let's go back to our 10x problem. If I wanted to integrate that, I would add 1 to the power, and then I would divide by that power. And I would get my final answer. Don't forget your C. So add 1 and divide. It's the opposite of subtract 1 and multiply. Okay? All right. Now, just something I realized I didn't really spend a whole lot of discussion on here. I want you guys to notice a subtle difference here. Do you guys notice this is a lowercase f and this is an uppercase f? That's not by accident. I used the same letter, f, to indicate that those are related to each other. This is the integrand, and this is the antiderivative of that integrand. So what we do in calculus is we use lowercase function notation for integrands, and we use uppercase notation for antiderivatives. Okay? And the reason I thought that is because when I saw this over here, if I want to take the integral of the integrand, that's the same thing as a big F. So I could have, instead of using this, I could just put big F here. So if you integrate little f, you get big F. In other words, if you integrate the integrand, you get the antiderivative. So there it is. Let's go ahead and take a look at some additional little rules here. Now, a lot of these rules don't really, they're not a huge deal. This looks horribly confusing. So I don't want to confuse you guys too much. So let's start with something that we already know, okay? The constant multiple rule. Remember how we talked about if you have a function with a constant multiple, when you take the derivative of that thing, the constant multiple just stays there. You take the derivative of the rest of it like normal, but that multiple just stays there. That's the constant multiple rule. Well, the same thing applies to integrals. When you're integrating a function that has a constant multiple in the front, you can just take it out and put it in the front. You don't even have to worry about it. It just stays there. The integral does not affect it. Okay? Now let's take a look at another one. We learned the rule for taking the derivative of a bunch of functions being added or subtracted. All you do is you take the derivative of each one separately, right? Same thing for integrals. If you're integrating a bunch of different functions to get being added together, we'll just take the integral of each one separately, okay? So my point here is that since integrals are the opposite of derivatives, a lot of the rules that work for derivatives are going to work pretty much in the same way for integrals. Okay, so knowing all that, let's go ahead and let's get started here. So I'm going to do an example with you guys. Let's go ahead and start with number 1. We're going to start easy, and we're going to work our way up to some more challenging stuff. So go ahead and take a look at number 1 with me. All right, my integrand is 12x squared. I'm integrating with respect to x, and I know that I'm integrating because I have my integral symbol there. Okay. Now, interpretation. This is a derivative. What was the function before I found its derivative? Okay, so here we go. Here's the process. We're going to add 1 to the power, and then we're going to divide by that number. And don't forget your plus c. I'm going to reduce, of course, and then we're all done. And you can check your work. What's the derivative of 4x cubed plus some random number that I don't know? Well, it would be 12x squared, which is what it should be. Okay, so that is that one. I wonder if I have student practice already made. I do. So I want you guys to go ahead and try this one. Pause the video and see if you guys can get the answer for that problem. There you go. You should have gotten 2x to the 4th plus c. All right, let's go back and take a look at another problem. What we're going to do is we're just going to kind of make them a little bit more interesting and challenging as we go. So I'm going to do 2 problems before I let you guys do the next one. So and the next one I'm going to make up, it's not going to be one of these problems, so I'll just make up a new one. I'll call it number 7, even though we don't have number 7 yet. So let's say I gave us this. What is the integral of 7 with respect to x? Well, that's just a constant, okay? Now there's an easy way to do this and a hard way. I'm going to show you the easy way. Anytime there's just a number here, the answer is just going to be the same thing but with an x next to it. Okay, that's the easy way. But I want you guys to understand that the power rule actually works. If there's no x there, that means it's x to the 0 power, which means that if you integrate that, you're going to add 1 to the power, and you're going to divide by that number, which still gives you 7x. It's just that it's a lot easier to remember. If it's just a number, put an x next to it. You're good to go. Now, if this wasn't an x, like let's say this was an a, let's say we had this, well, then you put an a next to it. And don't forget your plus c. That always needs to be there. Okay, so there's that. Now let's jump down to number 5. On number 5, we have a bunch of them being added together. But when that happens, you just do the integral of each one separately. That's it. It's not a big deal. So just like when you're doing a derivative of a bunch of things being added together, you take the derivative of each one separately. Well, when you're doing the integral of a bunch of things being added together, you just do the integral of each one separately. So for the first one, to integrate it, I'm going to add 1 to my power. And then I'm going to divide by that number. Next one, add 1 to my power. And divide by that number. Last one, this is just a constant. What do we do when we integrate a constant? You just put an x next to it. Finally, don't forget your plus c. Okay? Of course, I want you to reduce. So 24 divided by 6 is negative 4. 20 divided by 4 is 5. And once again, you can just check your work by taking the derivative of this thing, and you should end up with the original integrand there. Okay? Now I want you guys to notice something too. This symbol is like a command. It's telling you to do something. It's telling you to integrate these things. So after I integrate it, notice the symbol's not there anymore. I got rid of the integral symbol because I did it. The command's been executed. So after you take the integral, get rid of that symbol. Okay. All right. Your guys' turn to try one. I'd like you guys to do number 5 on your paper there. So go ahead and pause the video there and try number 5. Okay. There you go. All right, let's move on to another type of problem. So we've talked about the basic idea. We've talked about how to deal with constants and then a bunch of them being added together. Let's go on to some of the weirder ones like the fractions and the radicals and things like that. So let's start with number 2. Just like when we're working with derivatives, we always want to start by rewriting it. And I want you guys to understand, when I rewrite it, I'm not doing calculus yet. I'm just rewriting it so it's calculus friendly. So I don't like this 2 on the bottom for my power rule. So I'm going to put it on the top. And that makes the power become negative. Now notice that I still have the integral symbol there. Why? Because I didn't take the integral yet. I just rewrote it using pre-calculus. Okay? So now I'm going to do the calculus. Now I'm going to do the integration. All right? So I'm going to add 1 to my power. Now be careful here. What do you get if you add 1 to a negative 2? You actually get negative 1. Be careful there with your negatives. And then we divide by that number. Don't forget your plus c. Well, negative 2 divided by negative 1 becomes positive 2. And we could write our answer like that. But what's another way we could write our answer without a negative exponent? We could also write it like this. Either one of those are acceptable. You do want to make sure you know how to do both, because I don't know how it's going to look on your multiple choice test. It could be either way. All right? So that's how we deal with these kind where you have powers in the denominator. There's one exception though, but I'll tell you about that one in a minute. For now, let's have you guys try one. Oh, I did the student practice, silly me. Oh well. Why don't you guys do the teacher example then? You guys do number 2 here. Pause the video and try to do number 2 and see what you guys get. All right, so there we go. I started by rewriting it, then I applied the power rule, and then I reduced and I wrote it without a negative exponent as well. So the 2 different ways of writing your answer are there. All right, let's go ahead and move on to another type of question. So we know how to deal with the basic idea of applying the power rule. We know how to apply the power rule to a big string of numbers being added together as well as constants. And now we know how to deal with the power rule when it comes to these fractioning looking ones. Let's talk about radicals. Well, you're not going to be surprised to realize that just like we did with derivatives, we're going to start by rewriting it. Once again, that's not calculus. That's just rewriting it. That's all it is. The cube root of x squared can be rewritten as x to the 2/3 power. Okay? Now what are we going to do? Okay. Well, we're going to apply the power rule. So what's the power rule? The power rule is we're going to add 1 to the power, and then we're going to divide by that. Now, don't write this yet, because I want to show you guys a shortcut. Now, you could do this the long way, just like we had when we were doing derivatives. You could start like that. Then you can get a common denominator, and then you can add, right? But the faster way to do it is, remember when we did derivatives, it was just top minus bottom? Well, when you're doing integrals, it's top plus bottom. So 2 plus 3 is 5, and the bottom is 3. So if you want to add 1, just do the shortcut, okay? It's much easier. So we add 1 to this. How do we do that? Top plus bottom is 5, divided by the denominator, which is 3. And then we're going to put that same thing underneath. Okay, now you guys are really frustrated. Like, okay, what the heck is that, Mr. Bailey? Okay, well, let's talk about fractions some more, real quick. What is 1? Well, let's actually say, what's 5? What's 5 divided by 5/3? Well, as you guys know, we do keep, change, flip, right? So here's my point in saying this. When you're dividing by a fraction, that's the same thing as multiplying by its reciprocal, right? So how about instead of writing divided by 5/3, why don't we say times 3/5? It'll make things a little bit easier. Don't forget your plus C. All right, so we learned a couple of things here. First of all, rewrite. Second of all, add 1 using the shortcut, top plus bottom. Third of all, when you divide by a fraction, instead of dividing by a fraction, just multiply by its reciprocal. It'll save you a little bit of time. We're almost done. Let's go ahead and simplify this. We have 3/5 times 5 over 1. The 5's cancel, right? So what you're left with then is negative 3x to the 5/3 plus c. So I think I better do one more of those because there's a lot going on there. So let me do one more problem like that, okay? We'll call it number 8. All right, so suppose I asked you guys to find the integral of 2, and let's say the 5th root of x cubed. 2 5th root of x cubed. All right, well, step 1 is to rewrite it. No calculus yet. Now we do the calculus. Step 2 is to add 1 to the power. Our shortcut is top plus bottom, divided by bottom, divided by that number. But I don't want to divide by 8/5, so instead, to make my life easier, I'm going to multiply by the reciprocal. Don't forget your plus c. Now 2 goes into 8 4 times, and you're left with 5/4 x to the 8/5 power plus c. Okay? And there you go. So I'm going to let you guys try one of those. Let's have you guys try. Let's start with something a little simpler first here. Let me give you guys this. How about the integral of 5 and let's say 3rd root of x. Go ahead and do that one first. After you do that one, do this one. Okay? Pause the video and give it a shot. All right, so we got our 2 answers over there on the side. One thing that makes number 7 a little bit different is that nothing cancels, right? So we just multiply straight across. 5 times 3 and 4 times 1 is 15 over 4. For the number 8, on the other hand, we already had a number down there in the bottom, but it doesn't really change any of the process. You still add 1 to your power, so you get 7/5. You still multiply by the reciprocal. And in this case, the 5 and the 7 cancel, leaving you with just a negative. So you're left with negative x to the 7/5 power plus c. All right, what's next? All right, so this next one's really not all that special. It's really just kind of a repeat. It just looks ugly. It's actually the same thing as these kind. It's just that we don't have to start by rewriting it. It's already rewritten. Okay, so if I wanted to find the integral of this, I would start by adding 1 to the power. So 4 plus 3 is 7. Keep the denominator the same. Multiply by the reciprocal, because I don't want to divide by a fraction. Don't forget your plus c. 3's cancel. 7 goes into 14 twice. So we have 2x to the 7/3 power plus c. So not really much special there. It's just more of the same. So therefore, if you feel like you don't need to practice that one because you've got it, that's fine. I'll still offer you the opportunity, but if you want to fast forward to our last one, you can. But go ahead and pause the video here if you're interested in doing number 4, and when you unpause it, you'll see the solution. All right, so there's our answer for number 4. Let's go ahead and do one more here. Number 6. Not much new to discuss here. All it is combining what we learned over here with all the other stuff that we learned with these other problems into one. Okay, so it's just basically a nice way to end all this chat about this. So it's kind of got a little bit of everything in it. So how do we do this one? Well, since we just have a whole bunch of different pieces being added together, the way we handle that is you just take the integral of each one separately. But before we begin, I want to rewrite some stuff. I don't like the way that this one is written, so I'm going to rewrite it as x to the 1/4 power. I don't like the way that this one is written, so I'm going to rewrite that as x to the -4 power. Okay? Now that we have rewritten them so they're power rule ready, we can go ahead and apply the power rule. So the integral of this thing will be 25x to the 5th over 5. The power rule of the next one will be 15x to the 5/4 over 4 times the reciprocal of the power. I gotta squish that in there. Minus, add 1 to the power for this guy, get x to the -3, and then we're going to divide by that number, -3. And remember, we went back to division for that one because it's not a fraction anymore. All right, now we get to simplify a little bit. So here, 25 over 5 is 5. Here, the 4's cancel, and the 5 goes into 15 3 times. Here, the 3's cancel, but notice that there's a double negative, so that one's actually going to become a positive now. And the x to the -3, I wouldn't leave it like that, although you could. Let's not forget our plus c. But they'll probably rewrite that x to the -3 as 1 over x to the 3rd, but technically it would have been fine either way. In the same way, you could write this one here as a radical again, but my guess is that's probably how they would write it on the answer key. But anyway, so there's all that fun stuff. And that takes care of our lesson for today. So you guys just kind of get practice reviewing what all that notation is and how to apply it to find antiderivatives. Till next time, we'll see you then.